random quietness. I spoke too soon. I'll begin with a word of prayer. So, ahem. Hem. 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 I can't whistle, so this is all I got.
Hello.
All right, I'm going to start class now. So, Heavenly Father, we thank you for this day. Again, I thank you for this class. Just pray that you be with us today. Help us to glorify you what we do. And I just pray that we'd understand more about your creation together, Lord. In your name I pray, Lord Jesus. Amen. All right. So, let me begin with an example. Hopefully it will make some of the things I did last time come together, perhaps. So, example 1. We're given A is equal to, let us say, minus 2, comma 1. And we're given that B has magnitude 10 at standard angle theta equals to, I don't know, let us say 30 degrees. All right, so then find the magnitude and direction in terms of standard angle for C, which is equal to A plus 2 times B. All right. So when I'm faced with a problem like this, I might try to just draw a quick picture of it just to gain an understanding of like more or less what am I looking at, what should I expect geometrically, right? So we try to picture what's going on here to start with. All right, so A is minus 2, 1. So that means it's going 2 to the left and 1 up. So maybe that's something like this, roughly speaking. There's my vector A, right? Then how about the vector 2b? Well, b is at 30 degrees, right? So if this is A, 2b, so it's length 20 at 30 degrees. So I can picture that like here. So I've got like 30 degrees off that horizontal line. And I mean, this is something like 2b, all right? So I'm expecting that, where should C be geometrically? First quadrant, right? So I can picture it. Something like this is my C, right? And again, this is that tip-to-tail vector addition business I was talking about last time. So A plus 2B, but that doesn't really help us answer the question, So our goal is to find the length of the green line, right? And also to find this angle here. So the way we're going to do that is we're going to break A and B into components, all right? We're going to break A and B into components. Well, actually, we're going to break A and 2B into components, truth be told. So let's see here. As a point of organization, I'll put a little table right here, and we'll put A in this one, and we'll put 2B over here. All right, this will be X, and this will be the Y. All right. Let's see here. Oh, I'm sorry, I'm an idiot. Let's do this again. So sorry, guys. I've forgotten my ways. Put A over here. Duh. Put 2B over here. Let's make this X. Let's make this Y. And then down here, we will find the components to what we're interested in. Right, down here we'll have our C, which is A plus 2B. All right. Now, this table is really easy to fill out for the A, for the row that's A, right? Because what I gave you A in its Cartesian form already, right? So we can just simply write down A sub x is minus 2, A sub y is 1, right? That's fine. How do I figure out what 2b is? So what we got is we have, 2 times b for the magnitude, which is 20, right? This angle is 30 degrees. So that gives me this distance here is what? Okay, so I heard a 20 times cosine, right? And this up here would be what? 20 times sine, right? I happen to know that sine of 30 is 0.5, so this is 10. And cosine of 30 is about 0.866. So let me use a calculator. As a point of order, I try to keep 4 significant digits for answers. And I shouldn't say significant. I try to keep 4 digits for answers. The issue of significant digits is not one that I'm finding significantly interesting for this course. I will leave that to your chemistry course or whatever. I'll tell you what will get me wrong. All right, so here's what I get to start with. 3.085. But this is wrong. You know why it's wrong?
You're in radian.
I'm in radian mode. Very good. We need to be in degree mode. If I can shift over to... come on. I'll find it eventually. 3. So 20 times the cosine of 30. Of course, cosine of 30 is root 3 over 2. But we'd like to... This is technically 10 root 3, but this is physics, so I don't like 10 root 3 so much as I like 17, let's say 0.321. So if I want a 4-digit answer, if I keep 5 digits for calculations, then I'm usually pretty good, all right? So I'm not probably going to fuss about the last digit too much in here. But anyway, there it is. So our x component, this is the x component of 2b is 17.321. And the y component is 10. All right. Now c, the a plus 2b vector, I simply get the components of that by adding the x components and the y components respectively, right? That's our definition of vector addition. So this gives me a 15.321, and this gives me an 11. So I find that c is 15.321, comma 11. Now that's not the answer yet. Okay, so if I asked for you to find the vector c, period, and I didn't put on you find the magnitude and direction, you'd be done. This would be the answer, right? But we asked to find the magnitude and direction, so we need to do that. Magnitude is easy. C is the square root of 15.321 squared plus 11 squared. And this time that angle theta is going to be the inverse tangent of 11 over 15.321. All right. So we can figure out what that is. Square. I get 20.52 for the magnitude. So there you go. This is the magnitude. I can't spell. And magnitude and inverse tangent. What do I got? I've got 35.68 degrees. There's my standard angle, which I think, up to the limits of my artistry, it kind of makes sense, right? The length of the green vector is a little bit longer than the length of the red vector. I don't know if you can see that in the picture, but yeah. Any questions? Yeah.
Is there a unit we should give for magnitude? Or?
We're working at the moment with dimensionless, unitless, if you will, vectors. And this is where we start. Of course, in practice, we'll not too long from now be talking about forces and position and so forth, and velocity and acceleration. And so as a general point of order, a vector will have components that will have a certain dimension, and the magnitude must also have that same dimension. Because if you look at the formula, you know, if every component had like a meters, you'd end up with like the square root of meters squared, which would land you back with a meter again, right? Or you could have a vector which every component has feet. But as often is the case in math, we just work with a dimensionless coordinate system, right? We just have like 1, 2, 3, 4. We never tell you, is that centimeters, is that inches, right? Because it's up to you. You can choose a coordinate system, but yeah.
Do you check your math for the magnitude? I'm getting a different answer.
Do.
I'm getting 18.
Yeah, I think you're right. Yeah, 18.86. Thank you. Excellent. I wonder what I did. Anyway, excellent question. Well, correction.
Oh, sorry about that.
No, I mean, it's good. I would prefer this so much more than after class coming up to me going, hey, I think example one had an error in it. Like, no, this is the time. Perfect. Like, thank you. I welcome corrections. If I make mistakes, let me know. It is perfectly fine to find these things. So yes, tell you what, let us do a slightly more physical example, and I'll introduce another concept. All right. So, definition. If P and Q are points in Rn, then PQ is equal to Q minus P. It's the vector from P to Q. So like, we draw a picture of what's going on here. So let's see here. Maybe this is P, all right? And over here is Q. Right? So PQ is, oh man. Oh, I'm an idiot. Goodness gracious. Oh, wait a minute. We'll be tricked. Got to get my shirt. Yeah, let's try that. Let's try that over. Yeah. I think my standard notation is P minus Q actually. All right. So like the end point. Oh, good gracious. From Q. I'll eventually get it, guys. From Q to P. All right, so, I mean, obviously you got choices for how you make this definition, right? But this right here is that vector. See, PQ. Endpoint P, so it goes from, oh man, now I'm doubting myself. Goodness gracious. One moment. This is kind of like, like you're writing a paper or something, and this is hard for you guys to imagine, but imagine a world without spell check. and then you become convinced that you've misspelled a word, but you're not sure, you know? But every time you look at it, it looks like it's spelled wrong. And then finally you find a way to check it, and in fact it was right the whole time. But it just starts to feel wrong. I have that feeling right now, so let me just, give me a second here. Every time what?
I try and spell the word school.
Every time you try to spell the word school?
Why did I see it?
Schul. Let's see here. Atrocity. Let's see here. One second, guys. Come on. I know it's in here. Oh, seriously? Eh. All right. No, I was right the first time. In my notes on page 9, I define PQ to be Q minus P. I just talked myself out of it. So like my default was right. Sorry about that. So this is the vector from P to Q. From P to Q. Yeah, from P to Q. So my picture is currently, it goes from P to Q, so my arrow is supposed to be over here, right? All right, now that we got that. So listen, there's also something we can think about here, which is the vector from the origin, right? So like this vector here is vector P, right? Thinking of P as a vector from the origin as opposed to a point. That's the P vector, right? And over here, this is the Q vector, right? So can you see any kind of vector addition here? How about this? So PQ, if I do vector P plus the PQ vector, what should I get? Follow my picture here. So I go P up here, PQ like that. That's the same as doing what? Just Q, right? So that should be equal to Q. So notice that the formula gives us PQ is equal to vector Q minus vector P. All right, so there you go. This has a name also, like, so if we, so this is just geometry at the moment, but definition, if, let's say R1 and R2 are positions, position vectors, then the displacement from R1 to R2 is delta R, which in this case would be R2 minus R1. So in terms of like making a connection between these two discussions, you can think of R1 being like the P, you know, and R2 is kind of like the Q there, right? And PQ is the displacement from the point P to the point Q. Now the reason I'm doing this example right now is when you guys asked a question about units, I wanted to do an example with units, all right? So like, in contrast, the distance from R1 to R2 is what? The magnitude of the displacement, right? So that'd be the length of R2 minus R1. So let me give a specific example here. Example 2. So let's So we haven't talked about this yet, but for positions in physical space, we have to choose a coordinate system, right? So how do you set up a coordinate system? A coordinate system is some way of measuring distance from an origin. And we choose to measure it in an ortholinear way, which is to say that there's 3 directions and they're perpendicular. Whatever that means, we haven't really defined that yet, right? But you know what it means, right? Right angle between the directions. So if I choose the origin to be like here, let's say that the origin is this corner of the board right here, all right? And, I go something like this way is, let's say, Z. This way is Y. And if you can imagine it, the X coordinate axis there, it's coming out at you, all right? It's coming out at you. So, right here. So there's the X coordinate axis coming out at you. This is where 0, 0, 0 is, right here on the board. Are you with me? So then we could try to let's see here. That right there. Yeah, I'll try not to get you in the eye. But if we, shoot that point right there, you guys see it? What's your name?
Caden.
Caden. So Caden's shoulder. I guess it depends on what kind of units we use, but let's see here, 1, 2, something like 2 meters this way, and maybe 3 meters that way. So I think, let's call that R1. And where are we? Something like what? I said maybe about 3 meters in the X, so we'll say 3 meters for X. And how about Y? Oh, we're negative Y, aren't we? So minus 2 meters for Y. How do you think his shoulder fares against the place where I said the origin is here? Wait a minute, what am I doing? I got a laser. We can figure it out. I'll use a less dangerous laser. Oh, well, no, I was going to... Yeah, this seems safer.
That's a little bit safer.
So, of course, the question is, I'm actually holding the laser level, right? But, so it's 0, all right? Up to the limits of my sample here. Now, of course, you can buy laser levels, can't you? Like, I have one. It makes like a nice square, like a nice, cross that you can, hang drywall off of and junk. There are laser measurers too now, right? We use lasers to take measurements. That's one way you might set up a coordinate system, right? Is using that kind of laser technology, for example. All right, so that's the position of your shoulder. And let's see, I need to pick on somebody else. So, what's your name? Ruth. Ruth is right in front of the camera. So, I'm going to guesstimate you're 1, 2, maybe 3 over. It looks like you're 4 back. And I think we're going to use your shoulder, which is the same as, well, this is not very, you know what, we're going to assume you're taller. So for the purposes of this example being more interesting, you're going to be at 4 meters, and you're at 3 meters over this way. And we're going to say that you're 1 meter, you're very tall, actually, for the purposes of this example. All right, and then we can calculate what's the displacement between Caleb's shoulder and extended Ruth. So, so here we go. Displacement would be, 3 meters minus 2 meters. Let me get to the point here. I need to write so much. So we've got 3 minus 4 meters, and then minus 2 meters minus 3 meters, and then 0 minus 1 meter. This would be, what I'm calculating right now is R1 minus R2. Oh man, seriously? This is what I get for just a second. That's not the opposite of what I wanted to write. Sorry guys. Let's try that again. All right, so R2 minus R1, which is what? So we have 4 minus 3 is 1 meter. right? 3 minus a minus 2 is what? 5 meters. And then 1 minus 0 is 1 meter. Or you could write this like this: 1, 5, 1, and pull the meter out here if you like. That is the displacement vector from Caleb to Ruth, right? How far apart are they? That would be the distance from the shoulder to the extension of Ruth. Let's see here. So we're talking about square root of 1 squared plus 5 squared plus 1 squared. And we've got a meter out there. And that gives me square root of 27 meters, which is what? Wait a minute. Phone. Sorry, picking up the wrong electronic device. 5.2-ish. Now, of course, this is, very, very, very rough, right? Because my methods of measurement were very crude, but there you go. So yes, I mean, generally speaking, vectors are going to have units in them, but for the sake of focusing on the mathematics, that's the last I'm going to talk about units for a while. All right? Well, not too long, probably half hour. Any questions? Yeah.
What's the difference between what we have up there with the distance from R1 to R2 and what we just did?
This is the displacement. This is the distance. Displacement is a vector. Distance is a number or a scalar. These are very different, right? There's a whole infinity of points that are distance 5.1 from Caleb's shoulder, right? You're just like extended U is just one of those, but there's like a whole sphere of points that are all this distance, but there's only one that's that particular displacement from his shoulder relative to that coordinate system.
But up there it gives this definition for distance. The distance from R1 is right under.
Oh, I'm sorry. I'm missing a delta. I see you. Thank you. I'm missing a, yeah. That's the change in the position, the displacement.
Okay, so do we get that from calculating?
Oh, where's this coming from? This is 4 minus 3 was 1.
You have the same calculation for both displacement and distance in your definition, but in your calculations, one is the Pythagorean theorem, and then the other is...
I don't understand.
Right, so in the definition for distance up there, you have this R2 minus R1, but then down here we did Pythagorean theorem.
Well, yeah, but what's the length of a vector? It's the square root of the sums of the squares. We derived this at the end of last class. So I'm using what we did last class, which was that the length, right, the length of a vector is the square root of like a1 squared plus a2 squared plus a3 squared. And this time my a, quote unquote, is the delta r, right? So I'm applying that definition of vector distance. That's how I'm doing the calculation. It's the length of a three-dimensional vector, sum of the squares of the distances. So, okay, now I got you. I mean, do ask questions. If one of you doesn't understand, 10 of you don't understand, probably. This is your class. You guys ask questions, and I'll try to answer them. I'd say there are no bad questions, but that's just not honest. It's just not true, right? Okay, so next up, definition. Given A and B in Rn, we define A dot B to be equal to the summation I equals 1 to n of A sub I, B sub I. All right? This is the dot product of A and B. So this is just a notation for like A1, B1 plus A2, B2 plus dot, 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 plus A, N, B, N, right? It's just that notation. So if we're in 2 dimensions, there's just 2 terms. If we're in 3 dimensions, there's 3 terms. If we're in n dimensions, I'm misbehaving. So, I mean, we're not going to do n-dimensional physics in here too much, but I do try to say a word or two about where, you know, everything we... There are certain aspects of this course which are readily make sense in n dimensions. This is one of them. And so what I'm about to write is not the definition of dot product, but this is actually a somewhat deep theorem. And the theorem says this, that this is actually equal to A times B times the cosine of the angle between them. This right here is a theorem. And it's pretty much logically equivalent to the law of cosines. You can derive this theorem by imagining the plane in which the vectors A and B reside and working out what the effect of the law of cosines is in that plane. And then you can prove that the angle here is the same as the angle that the law of cosines gives you. These are in my Calculus 3 notes if you really want to look at it. I won't do that in here. Okay, so that actually defines for us then this angle between the vectors. So if this is like vector A and this is vector B, the angle between them, theta, is given to us by the dot product. Okay? And I used this word perpendicular like 5 minutes ago as if you know what it means, but now I can give you a specific definition. We say A is perpendicular to B. That's interchangeable with, you can either look at it as the angle between them is 90 degrees, if you like that, right? But you guys think about it. If the angle is 90 degrees, and you believe this theorem, you should, it's true. What's cosine of 90? It's 0, right? So what does that mean? If A and B are perpendicular vectors, their dot product is 0. Yay. So A dot B equals to 0. This is, you know, definition. So let me give you some examples of all this. So example 3, if we had A equals to, let's say, 1, 2, 3, and we had B equals to 2, minus 1, 0. All right. Let's calculate the magnitude of A, and let's calculate the magnitude of B. Let's calculate the dot product. Let's find the angle between these vectors. So you guys tell me, what's A equal to? The length of A. So 14, right? And what's the length of B equal to? 4 plus 1, square root of 5. Right? What's A dot B equal to? So we do 1 times 2 plus 2 times minus 1 plus 3 times 0. So this is just like A1, B1 plus A2, B2 plus A3, B3, all right? The dot product is a number, all right? We take two vectors in rather, and we get out a number. In this case, the number is number 0. Haha, so apparently A is perpendicular to B. The angle between them is what? 90 degrees. So, yeah, there's not much more to see here about that, I guess. I mean, this one, we didn't actually need to calculate the magnitudes for this, did we? You see that? We could have figured this out without calculating the magnitudes. But let's do one where we have an angle other than 90 degrees, see how that goes. So, example 4. Let's suppose we've got C equals to, let's say, minus 1, 3, 4. I would like for us to find the angle between C and A. So this notation is just a shorthand. So I'm looking at the angle from C to A. Do you guys see that notation? If you'd like, you could write out angle from C to A. So let's work this out. And I'm still using the same A from example 3, okay? So what's the magnitude of C? Minus 1 squared plus 3 squared plus 4 squared. That's the square root of 26, right? And what is A dot C equal to? So we should do A1 C1 plus A2 C2 plus A3 C3. What is that here, though? So we've got 1 times minus 1 plus 2 times 3 plus 3 times 4. So what's the dot product of A and C here? I heard of 17. I'll buy it. 17. But we also have this theorem, right? And the theorem says that A dot C is also equal to what? It's equal to AC times the cosine of the angle we don't know. Right? So AC cosine theta is equal to 17, which tells me that cosine theta is 17 over AC. Now what is AC? We know what it is. A is the square root of 14. And C is what? Well, C is the square root of 26. So what does this make theta? Can you guys see when I'm right? Is this too far down? Can you guys not even see me? Are you still okay at the moment, but any lower is bad?
Any lower would be bad.
Can't even see it? Err.
Is that thing weird?
Now it's a problem for you. Yeah. Huh. Well. Now it's just a problem for the janitors. Let's see here. Okay, so now everyone can see? All right. Well, if you need to stand up, go ahead. Maybe you should get a periscope. Some of you are using your phones like a periscope. I like it. Okay, anyway, so I'll put the math up here. We've got theta then is inverse cosine of 17 divided by square root of 14 times the square root of 26. Right, so theta is actually equal to, what's the angle between A and C here? By the way, the square root of a product is the product. I mean, you can bring the 14 times 26 inside one square root if you want for the calculation. I am getting, whoa, that's cool, 27.00 degrees. I could have made that happen if I wanted to. It's actually 26.9955084 on my calculator, but whatever. Are we good? So, can you picture these vectors? I mean, you could, right? You could draw an XYZ coordinate system and try to like visualize where these vectors are pointing, but I would point out that we don't need to because we can use the dot product to calculate the angle between vectors in 3 dimensions analytically. This is pretty cool. Now let me point out some more to you here. If I can find my eraser shirt. So can you guys see anything that we can say about this dot product here? Like, let me point out some things about the dot product that are extremely interesting and helpful. So we can write a formula for the length in terms of the dot product. Notice that the length of the vector, A, is exactly equal to the square root of the dot product of A with itself. Right? So that's one thing we can say. So here's some nice formulas from dot product. So first and foremost is like the length of vector A is actually the square root of the dot product of the vector with itself, right? Because that is exactly A1 times A1 plus A2 times A2 plus A3 times A3, right? What else can we notice? What if I take A dot x hat? What's that equal to? We'll keep it three-dimensional here. All right. So x hat in 3 dimensions is 1, 0, 0. What happens when we take the dot product of A with x hat? What happens when we take the dot product of A with y hat? What happens when we take the dot product of A with z hat? So you guys tell me what happens. What do we get?
We just get A1.
A1, all right. And then A2, right? And then A3. In other words, the dot product with the unit vector in the direction, it selects the component of the vector in that direction. So if I look at it, I can write A is A dot x hat times x hat plus A dot y hat times y hat plus A dot z hat times z hat. This right here, this first piece is the x vector component of A. Right? In contrast, A dot x hat is just A1. This is the x, simply the x component of A. This is the scalar component in x direction. A scalar is a number, a vector is a vector. So any vector in 3 dimensions can be built from the piece of the vector that points in the x direction, the piece that goes in the y direction, the piece that goes in the z direction. I drew a picture last class that showed you how this works tip to tail, right? So I'll draw that picture again. Okay? So the part of the vector which points respectively in the x, y, and z directions, it's picked up by taking the dot products with the unit vectors in those directions. All right? But think about this. There's nothing really especially special about x, y, and z as, vectors, right? As directions, rather. See, what if I asked you a different question? What if I said, find the part of B which is pointing in the A direction. All right? And my notation for that would be projection in the A direction of B. All right? So I can draw a picture of this, perhaps, is helpful. Here's B. All right? And here's A, let's say. So what I'm describing right now is the part of B which points in the direction of A. So like if I draw that in the picture, if you draw a perpendicular bisector to A like this, right? Then this is the vector I'm after. Right? That would be projection in the A direction of B. What's the formula for it? Any ideas? I guess it's hard to see in my picture, but if I were to move this green vector back to the origin like this, that would be A dot z hat like that. See that? And that would be the projection of the A vector onto the z-axis. So the procedure is you take the vector, you dot product with the unit vector in the direction you're interested in, and then you multiply it by the unit vector of that direction. So this is projection in the z hat direction of A. That's what that is. So here, since we're talking about the B vector, we simply write A dot B hat times B hat. Now you're like, what's B hat? Well, we defined that last class. Remember what B hat was? We take B and we divide by the length of B. So in terms of a formula, you can also rewrite this as like A dot B vector divided by B dot B times B. This is the projection of one vector onto another. All right, so let me see how much time I got. I got just enough time to get into trouble. I'm not going to try to do one of those in the last 3 minutes. I'm going to do something more fun. So imagine you have a cube. And for sake of specificity, we'll make it a unit cube. All right, we'll make it a unit cube. All right, let me draw it. So I'll put my z-axis back here. I'll put my x-axis this away. I'll put my y-axis that away. All right? So like each one of these side lengths is 1. So my question to you is, what's the angle? I tried. So my question to you is, what's the angle between the back vertical leg here, which we'll call that A, and the vector and the the line that connects this front point to that? I'll call that B. So what would this angle theta be?
45.
I have a 45-degree guess. Thank you. That's what I was looking for. Let's see why that's wrong. So, so A is, no, every, I have done this like, I don't know, 10 different classes. Every time, without fail, somebody will guess 45. Because that's what you want to say, right? So A here, if this is a unit, so that A would be what vector? It would be 0, 0, 1, right? The B vector is what? You're going 1 over, 1 over, 1 up, so that's 1, 1, 1. Right? A dot B, what is it? A dot B is 1, because 1 is, 0 times 1 plus 0 times 1 plus 1 times 1, also known as 1. But that's also supposed to be equal to AB cosine of the angle we don't know, or we think it's 45. But what is A? A is 1, B, square root of 3. So this is equal to the square root of 3 times the cosine of the angle we don't know, which makes theta the inverse cosine of 1 over root 3. What is the inverse cosine of 1 over root 3? If memory serves me correctly, 54.7 degrees. Let's see if I'm right. Probably not. Stupid parenthesis. Oh, man. Come on, calculator. Too smart for your own good. Oh, 54.74. Now, why is this? So the reason I give this is to try to convince you that your intuition about geometry can deceive you. We should use vectors to understand questions about geometry in 3 dimensions, because analytic geometry, in as much as you apply it correctly, will give you correct answers. The reason that the 45-degree guess is wrong, if you look at this from the top down, right? You're looking at a vector that kind of goes like that. So if I drew just the diagonal, there is, so this would be like my A, and this would be like the B. So this has length 1, this has length root 3. So of course that angle is not 45 degrees, because the vertical plane which intersects the diagonal of the cube is not a square, it's a rectangle. Because one of the sides is a diagonal and the other is a side length. So it's not a square, that's why the diagonal is not a 45 degree. But, and if you, some of you probably might have seen that if I'd given you more than 3 seconds to think about it, right? But with vectors, we can calculate angles between, vectors in 3 dimensions with great success. I'm sorry, I seem to have gone time over, but in my defense, I started a minute late. So, sorry guys.